for improving the transient behavior, there is two method. One was PID Controller that was discussed in the last class, and this is the implementation of that. Now, today we are going to discuss the counterpart of it, which is implemented with the passive networks. So the lead compensator. So as we already know that the passive compensator is implemented with, the lead compensator is implemented with the passive networks. And because of the passive network, it is impossible to have a single isolated zero. So a combination of pole and zero is actually results produced. And so whatever the angle contribution, that has to be provided by the combination of the pole zero to shift or reshape the root locus. Okay, so it has two advantages. The first advantage is, since we are implementing with the passive network, it doesn't need any additional power supply, as well as the differentiation process actually introduces some noise that since it is not a pure differentiation process, so actually it will also the noise will be also reduced by some margin. And the disadvantage of the additional pole will be there here. Actually, the zero was actually trying to help the root locus from going towards the right half turn by crossing the j omega axis. But since you have a pole zero here, so this advantage will not be available that was available in the PID controller. Okay, so these are the introduction for your lag compensator. So, sorry, lead compensator. Then you have, okay, so what is the basic concept? The basic concept is, as we already said, that we are happy with we're not happy with our existing root locus. So basically, maybe we're somewhere here, our root locus was here, going through this point, but somehow we're not happy with it. So we prefer a particular point, desired point like this one. And then these are our existing system, zero and the poles. We have 1, 0, 2 poles. So now the contribution of those will be theta 3, theta 4, theta 5. Definitely, since we move to a different location, so the summation of theta 3, theta 4, actually since these are the pole angles, that has to be subtracted from your zero angle, that is theta 5. So this will no longer be an odd multiple of your 180 degrees. Okay, so that means this point here is not on the root locus. So for bringing it on the root locus, we have to figure out what is the rest of the angle contribution. So what is the contribution of the angle by these three? And we can subtract that value from this value, find out what additional angle we need. Say additional angle is needed is theta c. Okay, so theta c, since we are implementing with the passive network, it will not be provided by a single zero. Rather, we'll have a zero as well as a pole. So the contribution of this zero and the pole, that is theta 2 minus theta 1, is basically our contribution of theta c. So that theta c will give us the rest of the angle contribution needed to make this value equal to odd multiple of 180 degree. Is it okay? So this is how it works. Now the question is it only one possibility of having that contribution theta c, or we have multiple options? So for that, let us look at the next figure. It will be more clear from the next figure. Okay, so look at here. What you can see that theta c is the contribution needed, but it can be provided by multiple, actually infinite number of options we have. So we arbitrarily choose a pole, and then we see, we figure out what is the contribution of that one. Okay, and correspondingly we find out that pole value. Similarly, choose the next one, find out the corresponding pole value, choose the next one, find out so infinite number of location you can select as your zero location, then corresponding angle will give you theta c. Okay, so actually it has to be outside that boundary. Okay, so maybe it will go somewhere outside. Okay, so this is how you have to figure out what is the value of your theta c. Okay, so infinite number of choice. So which one you have to choose actually depends on various parameters like the gain value, or depends on the performance parameter like steady state error, how much is actually been changing. So all this steady state error, then gain adjustment, or maybe how difficult whether the second order approximation is valid or not. So all this actually are taken into consideration before choosing the point, which one is giving a better performance as well as better approximation. Actually, you have to go for that one. So it's a design criteria. You have to choose it by yourself, and then you have to see whether it fulfills our all the criteria or not. Now, let us look at this example, example 9.4, lead compensator design. So here, what the question says is, it says that uh, you have to have a reduction of the settling time, by a factor of 2, and you have to maintain 30% overshoot. Okay, so then you have to compare between 3 different designs. So actually you have to choose 3 different ZC, and correspondingly you have to find out that PC location, and then you have to check then calculate the rest of the system behavior parameters, and then you have to check whether the result is okay or not, whether they satisfy our criteria or not. Okay, so one thing that we already said in one of our previous videos as well, that actually nobody will ask you to figure out the root locus of the uncompensated system, but this is your first task to do. So figure out the root locus of the uncompensated system, or the given system, basically uncompensated system. Okay, so the figure, this is the same as the previous example, that is actually your G of S is K by S plus 4, the last example basically, S plus 6. Okay, so you have to plot the root locus, then you have to find out your zeta line, and then you have to find out that intersection point, because this is our starting point. So our intersection point is this minus 1.007 plus j 2.627. Okay, and you have to find out the corresponding value of k. We know how to find out the value of the k. All of this actually we already discussed. So this is k is actually product of the pole length divided by product of the zero length. But in our system, we only have pole length, so this will be just product of the pole lengths. Okay, so this is what you have to figure out. Now, so once you have figured out what is our sigma d of the intersection point, okay, so sigma d, okay, so that's sigma d will actually help us to find out our settling time TS. Okay, and from that TS we have to make that TS actually half of the existing one. That one will actually help us to find out the next value of sigma d. Okay, so from based on the sigma d, that we have to calculate what will be our new omega d. So it will correspond to this particular new point. Okay, so actually this calculation is being shown in the next slide, so let us go there. Okay, so based on the intersection point, actually zeta value is called calculated based on your percentage overshoot. So we already know the formula, that is minus ln percentage overshoot by 100 divided by square root of pi square plus ln square percentage overshoot by 100. So this is how you have to figure out the zeta value, and after finding out the zeta value, uh, zeta will actually help us to find out that line, isn't it? Because of the fact that cos theta equal to zeta. So theta will be cos inverse zeta. Okay, so as we said, the TS value you have to calculate. Okay, so based on your sigma d, so see whatever the sigma d you find, if we find out the TS value. Now new TS value has to be half of the previous value. So we calculated that, and now new sigma location has to be usually replaced by new TS, so it will be actually minus 2.010. It is actually how the double of this one. Okay. Oh, we could have just avoided the calculation, because if the settling time is a half, then your zeta location, because they're inverse, so it has to be double. Okay, so based on that, you can find out the omega d location, because we know that tan inverse, the angle. Okay, so tan, the angle contribution, is actually omega d by sigma d. So from that, if you know the sigma d, or you can find out the omega d. If the angle is known, angle is already known to us, because we already figure out from here theta. So theta, actually the angle will be 180 degree minus the theta. So that will give you 110.98, something like that. Okay, so if one is given and you know the angle, because it is always a constant percentage overshoot rate, so you can find out that and other one. So vice versa. So whatever given. So similarly, we can find out actually the location is now available. So we already figure out the real axis component. So real axis component is minus 2.014, and your imaginary axis component is J 5.252. And based on that, you can also calculate the value of the gain K. So whenever you have a new value of the gain K, you can always, new location you can always find out the value of the gain K. Okay, so now what will be the locations of your pole and the zero? So as we said, there is infinite number of solutions you have. So you have to choose a particular value of your pole, and then you have to you have to find out, assume a location of the zero, and based on that you have to find out the location of the pole. So how can we do that? Okay, so let us try to figure out the thing. So you have to choose a particular location, and actually the problem is asking you to find out not a particular location. They want you to do it for 3 consecutive locations. Okay, so and you have to compare the results. So first one they have actually taken is at location -5. So we assume that our ZC is equal to -5 location. So if it is at -5 location, so we can find out the contribution of all the points. Okay, so what was our transfer function will look like now? We actually have so far is S plus 5. Then we have S. Then you have S plus 4, S plus 6. And the one that we are trying to figure out is S plus EC. So, but okay, so this is not needed right now. So we'll discuss, we'll try to figure out this value. So now all these 0 and the other 3 pole, from that one, we can find out the angle contribution using the tan inverse formula. Okay, so tan inverse height by base. Okay. So if the angle is more than 90 degrees, then 180 degree minus. So that will give you a angle of contribution of minus 172.69. But we know that it has to be odd multiple of plus minus 180 degrees. So how much it differs? Actually, it is differs by minus 7.31 degrees. So that minus 7.31 degree has to be provided by this pole. So basically, out of the pole and the zero contribution, we are selecting the zero, and then we're finding out what the pole location should be. So again, the formula is very simple. Tan angle equal to your height by base. So base will be how much it is deviating from that pole location. So this from this one we can find out what will be the location of our PC. Now we can actually replace the PC here, and that will be 42.96. Okay, so okay, so this is your root locus now, how it looks like, the new root locus. Now what we have is we have a pole here. The black ones are actually open loop conditions. So because we are corresponding to a particular gain value whenever we are actually jumping to that crossover location. So whenever we are jumping to that particular gain value, then actually we are shifting. This one is shifting there. This one is shifting there. Okay, so these two are merging, and finally they are one going up and one going down. So this is our dominant second order poles. This one, this zero, higher order zero, is cancelled by nearby higher order pole for that particular value of gain, and this is the higher order pole, and this is far away from our dominant second order pole. What was our condition? The condition was it has to be 5 times away. Now it is more than that, way more than that. Okay, so this is your compensator A or at location -5 that we have seen, -5. Example, next one is we are placing it -4, and then I think the other one is places -2. So three different location, and as you can see, compensation 3, which is at -2, is actually deviating from the other two. Other two are actually more appropriate to the values of the result that we are looking for. And this one is actually representing our uncompensated system. This one is uncompensated. Okay, so let us compare the table and what values are actually changing based on your choice of zero location and correspondingly whatever the pole that you are calculating. Let us look at in the table. Okay, so this is your uncompensated systems system, the first one, first column. Okay, so this is your uncompensated system. This is whenever you your zero at -5, then we actually have shown the calculation for that one. So rest of them actually you have to do it by yourself. This two. So this one, as you can see, these are actually cancelling each other. We deliberately placed a zero at a pole location. So pole zero is being exactly cancelling each other. So what is left is a pure second order system, because this one is far away. So the approximation is valid. Okay, so as you can see, it is at -2 and it is at -20, so more than 10 times. What about the third one? Whenever we're placing the pole at -2, as you can see here at -2, and this is the higher order pole is this one, which is -8, which is not more than 5 times. So actually the pole, it doesn't apply the second order approximation. So because of that, what we have to do is for this particular case, you actually have to verify it by simulation. So simulation has to be there, otherwise we cannot be sure about the result. Now, rest of the thing, let us try to say, see which one is better. Okay, so settling time, they're following the same because we are maintaining same sigma value, so they're same. What about the peak time? So peak time is also almost same. They also have given the simulation. They also compared with the simulation the actual values. And what about the steady state error? As you can see, this one is actually giving better steady state, smaller value of steady state error compared to the other two. Okay, so this is a better design. And what about the zero locations? We calculated that, and higher the pole zero location. So this one is far away, and as well as this one is actually cancelling the 0. So basically the second order approximation is valid, and this one 0.0 is exactly cancelled, and the pole location is far away, 5 times away, actually 10 times away from the dominant second order pole. Here, and this is not the case. Okay, so in this particular case, we cannot be sure about the results, so we have to do the calculation again. So this is our lead compensator. So from infinite number of choices based on your desire, you have to choose a particular value of 0, and then you have to see whether this actually fulfills our rest of the design specification or not. Okay, so you can also see what are the variations. So k value is also a varying parameter here based on your design criteria. Okay, so let us look at the next. Let us now go to the next topic. Okay, so now we want to actually, this is article 9.5. We actually want to summarize, have a complete solution. Complete solution means we initially have seen the reduction of or elimination of steady state error, okay, as well as we have seen the desired, obtaining the desired uh, performance transient behavior using your PD and your lead compensator. So now actually we are interested about integrate both of them together. So if you integrate both of them together, so ideal compensator you're trying to use, then it is called PID controller, and the PID controller differentiator is for transient behavior, and ideal integral or pole at the origin actually will try to eliminate your steady state error. Similarly, if you want to implement it using the passive network, in that case you have lead compensator for transient behavior improvement, and you have lag compensator for reduction of the steady state error. So if you want to eliminate the steady state error completely, then there is no other choice. You have to go for the PID controller, or if you're happy with your reduction of the steady state error, in that case, you can actually omit the active networks with the additional power supplies. So we can go for the lag-led compensator. Okay, so let us begin with the PID controller. So how to implement the PID controller? Now, I'm not sure whether you have noticed or not. In case of the change in the transient behavior, or in case of the improvement in the transient behavior, your root locus is shifting. Okay, root locus, we are changing the root locus entirely. We are going to a different position. But in case of improving the steady state error, we are trying to keep it as in case of the similar root locus position. So what actually I'm trying to say here is, whether you have noticed or not, is that the improvement of the steady state error, for that we are actually not shifting the root locus. We are just introducing a pole at the origin and nearby 0. So it is almost at the same location. But for improvement of the transient behavior, we are actually shifting the point to a different location. So we are reshaping the root locus. So which one is better for us to implement? Okay, so which one is better for us? The first thing is, if you implement the steady state error first, then you shift the location, then you are not sure about the steady state error anymore. So you again have to calculate it. So that is why it is better to implement the shifting first. You shift it first, now you're happy with the criteria. Now you adjust your steady state error behavior. So that is why I actually go for the derivative controller first. Okay, so derivative controller first. It is ideally PD, or non-ideally, or with the passive network, lead compensator first. Then if you are happy with that, verified by the simulation or second order approximation, then we go for your integral controller. So integral controller, either elimination of the error, PI, or elimination, reduction of the error, your lag compensator. Okay, so this is the idea. So since we are designing the PID controller here, so we'll go for the PD controller. So and we figure out the desired location of the 0, and then we'll try to simulate the result. If we are happy with the result, then we proceed to design for PI. But if we are not happy, then we try to readjustment. And once it is the specification is or the requirements is met, then we go for the steady state error. So after finding out the steady state error, then we have to find out the value of K1, K2, K3, which is corresponding to the gain values here, pure gain or integral gain or derivative gain. So we have to figure out those values, K1, K2, K3, and then we have to actually resimulate and to check whether the finally every design parameter is okay or not. If it is okay, we are happy. Otherwise, we have to tune the values a bit to redesign the thing. Okay, so these are the simple steps that you have to follow. Okay, so look at this example 9.5. A particular system is given with 0 and 3 pole. What they're asking is you have to reduce the peak time by 2/3, and whatever the existing uncompensated peak time, that the new one has to be 2/3 of that, and also you have to maintain a particular percentage overshoot. Okay, so and also they're asking you to have 0 steady state error. So what are the criteria that we are finding is, first of all, this parameter given 2/3 of the peak time or maintaining percentage overshoot, this actually leads to a controller. Okay, so derivative controller. So which type of derivative controller actually help you to figure out from this one, because they are asking for 0 steady state error. So for 0 steady state error, you have to go for PI. So the derivative controller that you have to go for is actually D. So that is why you have to go for PID controller. Again, first thing first, you have to draw the root locus before proceeding further. So after plotting the root locus, you have to find out the zeta line. After finding the zeta line, you have to find out the intersection point. So from the intersection point, we are going to find out your sigma d and omega d. So this time, peak time is related to omega d. So you find out the new value of omega d nu maybe. Okay. So from that, you find out the sigma d nu. Okay. And then you find out your new location, and you have to check by calculating all the parameters whether the PD controller, okay, sorry, after finding out the point, you have to introduce the 0, okay, S plus ZC, okay, so of your PD controller. So find out the location of ZC based on your angle contribution, so that this new point becomes your on the new root locus. Okay, so after plotting it, after finding the point, then you have to figure out, calculate all the values of the table, the last table that you have seen. So if you're happy with the values, then we go for the calculation of your PI controller. Okay, so it depends on how much you have to have a pole at the origin and how close you want to make it. So it depends on you. You can make it 0.5 or 0.01 or 0.1. So based on that, your previous values of your PD controller will be more or less closer to that. Okay, so let us look how they have implemented, because we already have shown you detail how to calculate all the values. So this is why we are going very quickly with this example. Okay, so now here, as we already said, they have figured out the uncompensated system. Then they have figured out the blue line actually here is uncompensated systems root locus, this one. Okay, so they find out the root locus first, then find out zeta line, 20% overshoot zeta line. Then they figure out the intersection point. So based on that intersection point, they find out the new omega d, because the omega d, it has to be 2/3 of the previous TP time, so peak time. So basically, based on that, you can do the calculation that if you, as you know, if you know omega d, you can find out the sigma d because angle is already known. So angle is 117 point. So this is your two-step is already done, figuring out the new point. So after figuring out the new point, then you have to actually uh, figure out the zero location. Okay, so for that you have to find out the angle contribution of all the existing pole and zero to that new point. Okay, so this is what they have escaped, but you have to do it by yourself. Then you find out that this is the angle contribution to the new pole. So angle contribution of all the pole and zero of the existing system to the new point. And we know that the additional compensator zero has to be contributing so that it is closer to plus or minus 180 degrees. So the additional angle contribution is 18.37. So we know the formula, tan 18.37 is height by the base difference. So base difference, from that you can find out that your zero location has to be at 55.92. This is your PD controller that we have designed. So after PD controller being designed, actually you have to compare the table, complete the table. Then after completing the table, then you have to go for PI controller. Okay, so as we said, the PID controller is designing relatively easier. So you choose a pole at the origin and a nearby zero. So that nearby zero, this is not a bit farther, but this is how we are experimenting with. So the closer the better. So we can actually have taken this, or we could have taken this. Okay, so it doesn't make any difference. Bottom line, pole at the origin will actually eliminate the steady state error. Okay, so now the PID controller that we have is this. We actually have to be careful about the PD controller. Then the PI controller is just a suitable selection, and based on that, you can find out what should be your the value of your PID controller. Okay, so this is the final design value. Now, after having it, you have to figure out what should be the value of KI, K1, K2, and K3, and incorporating all of this, you have to actually plot the root locus again, and then you have to check whether all the performance parameter, those are you calculated, those are fulfilled or not. Okay, so let's look at the this. They have shown the new the root locus as well as your system behavior. Okay, so this is your root locus, the new root locus, new point zero of your PD controller here. And we have introduced a pole here, a pole at the origin that is related to your PI controller, and nearby zero. So these are related to your PI controller, so that the root locus is remaining unchanged. So this was uncompensated system. This was actually PD compensated system, which still the steady state error improved a bit, but it is not zero. Then after the introduction of your PI controller, now you have zero steady state error. Okay, so this is the step response of your system after PID controller being designed. Okay, so similarly, I think there was a table in the book. Somehow I failed to bring that here. So yeah, table 9.5. Okay, so you actually have to go through that. You have to generate that table 9.5, table 9.5. So this is your assignment. Okay, assignment, and assignment on this chapter. Example, actually, I think this is example 9.5. So complete the example 9.5. Okay, so this is the first part of your assignment. So task 1 is figuring out completely design without skipping any point, solving your example 9.5. Okay, so you may think that some of you will be doing it and then you just copy it, but I will suggest you not to do that. You try to understand everything and implement by yourself, because while I'll be taking the Viva, I'll maybe asking you to do the thing in that time. A small portion of that maybe whole uh, problem, I will try to figure it out. So if you fail to do that, then you will lose your assignment marks as well as your Viva marks. So I'll actually want you to do it by yourself, or understanding at least clearly. Okay, so now the passive counterpart of it, so that is lag lead compensator. So again, which one we should go for? We should go for the lead compensator. That means the reshaping of the root locus, that will be going first. After doing the reshaping of the root locus, then we'll focus on how much we want to reduce the steady state error. This time we cannot eliminate because it is not ideal integral controller. So basically, we have to figure out the corresponding value. So strategy saying, so derivative controllers first, then go for the integral controller. So passive network, so both of them are non-ideal compensator. And in the middle, after the steps are same as before. So after derivative controller, the lead compensator design, you have to check the result, whether the result is okay or not. If you are happy with it, then we go for the lag compensator. Okay, so the same example actually they have given. This is same as I think example 9.4. So for this one, you have to check. You have to design a lag lead compensator, and then you have to verify the result. So this is your assignment number 2. Assignment question 2. You have to also repeat this one. So you have to reproduce this one without skipping any line. Reproduce this one without skipping, without skipping any calculation. Okay, so this is a question number 2. Okay, so what does it says? It says twofold reduction in the settling time. So settling time has to be actually half percentage overshoot given, and you have to design a lag lead compensator. So steady state error criteria, they have given tenfold improvement. That means 10 times lesser steady state error has to be there, and your input is RAM, which is not necessary to give because of the fact that we know that our system type is 1, so it has to be RAM. Okay, so let us see how they are doing, how they are following this step. So as before, we already know we have to find out the root locus of the uncompensated system, and then based on you have to draw your zeta line. Then you have to find out your intersection point, and that intersection point is figured out here, and corresponding gain values. Okay, gain value is product of the pole length divided by the product of the zero length. All of you have actually shown you before. So we know the this time again settling time. So settling time is has to be half. So basically this value has to be double. So this is what is making double. Then you can find out what will be the corresponding value of omega d. So we find out the new location. So once this is our new location. So once we know the new location, then what you have to do, you have to choose a zero location. Okay, you have to choose a zero location, and as you know that angle contribution of the lead compensator will come from a zero and the pole, zero and pole. So zero has to be closer to the origin than the pole. Okay, so you have to assume one of them because you have infinite number of solutions. So assume one, and the other one will be coming from the calculation. So in this particular case, they're assuming it at -6 location. So after having the -6 and all the other -6, actually, if you look at your transfer function of this particular example, then actually we have s sorry, s plus 6. S plus 6, and our original function was s plus 6 and s plus 10. So basically bottom line is we're cancelling on pole 0. So we can also do that. We can choose a point at the location same as one of the poles, so that actually we can make it a pure second order approximation. But you have to be careful about the fact that we have another pole that has to be placed. So actually you have to find out the location of that pole. So to find out the location of the pole, the procedure is same as before. You have to find out the contribution of all the angles, basically this one and this one, and what is the difference between the contribution and plus or minus 180 degree. You have to figure it out. In this case, this is 15 degrees, 15.35, and based on that, where height is always same, we know that, so we can find out what will be the location of your PC, and this gives you location is -29. So this is -29.1. Okay, so this is your lead compensator design. So location of your new pole is more than 5 times away from your dominant second order pole. So we can say that our system is going to behave like an idea, like an approximate second order system. Okay, so now this is how it looks like after the zero bin design. Okay, so this is your lead compensated system. Okay, so you have to calculate the gain from that particular new point. The gain value you can calculate sum of the product of the pole lengths divided by the product of the zero lengths. So for simplicity, even though they are actually cancelling each other, but they actually kept in the root locus so that you can see that they have been cancelling each other. So these two are going to merge together to this break away point, and then you one will be going towards -60 degree line, one will be going towards 300 degree line, the other one is going towards your 180 degree line. So then you have your intersection point of the desired specification that you are looking for. So this is your lead compensated system. After the pole and the zero at 6 is being cancelled out, this is the left of your system. Oh, so they also have calculated your steady state error here. Okay, so steady state error of your lead compensated system, but we haven't done anything to reduce it. So you're just calculating so that it can help you to what is the existing value right now. Then based on that, you can figure out what will be the amount of reduction that you're looking for from your lag compensator. So you can find it, what will be the value of it. So basically KV you have to calculate because it is a type 1. So limit S tends to 0 S GLS LCS. Okay, so and that will give you four points of it. So okay, so now how to design the lead lag compensator. So in the middle, actually, you have to form the table. After forming the table, you have to verify whether the result is okay or not. Now, designing is a lag compensator is very simple. So you have to figure out the ratio of these two so that it gives you a 10 times lesser steady state error. Okay, so if you take this one and then 10 times lesser, and we will see have seen what is the value of the kV in the last slide. Okay, so based on that, you have to find out your new location and new values of your lag lead compensator system, and then you have to form the table again, and you have to compare the results, verify whether your design specification is properly met or not. For the lag compensator design, you can actually go back to your design problem that you have done before the Eid vacation. I'm trying to do it a bit fast because of the fact that there's still two more chapters left after this one, and we are actually having only 1 week left. So I'm very much nervous about the fact that how I'm going to finish the syllabus, and then your assessment is also will be a huge task. So that is why I'm trying to do a bit fast, but I'll appreciate you solving these two examples so that your idea has been clear. Okay, so this is your design specification. Now, okay, so go for the next one. Next slide. Now they're actually comparing the results here. So they're comparing the values of the uncompensated system and the lag-led compensated system, and they're also giving you the time response of with your input and the output, and they're just showing how much the steady state error is improved as well. So this is not possible in the exam hall to draw these curves, but this is only to show you the results. Maybe they'll be coming after you have your simulations. Okay, so now the comparison table is also being shown here. Now this table shows here is, this is the uncompensated one, the first one. Then you have the lead compensated or adjusting the transient behavior. Then you have your lag lead, basically we're reducing the steady state error. So let us look at the steady state error. So this is the steady state error of the lead compensator, which automatically decreased by certain number, but our target was, what was the original one? We have to reduce it 10 times lesser than that. This is ultimately been taken care of. Okay, so also TP value. So they are this one is better. Okay, so and also this is not that much change, because we know that after designing the lead compensator, lag compensator hardly contributes anything to the gain or your angle. So basically they are almost, you can see, close to each other. Okay. So only the improvement is in this segment, the steady state error. And what about this approximation? Approximation is valid because of the fact that this one is actually cancelling the pole and the zero. Since they're very close to each other, they'll be cancelling each other, and this one is far away from your dominant second order pole. So design specification is good. So what your task is to reproduce this table. Okay, so this is a question number 2 of your assignment. Okay, so this is a notch filter. This is a mechanical system, high frequency plant. So once you have a, this is just for your information. This is not that important for the exam. So what happens is sometimes if you have pole very close to the j omega axis, so there is always a possibility that they may cross the j omega axis and go into the unstable zone. So in this kind of plant, you have a very high frequency uh, like this. Okay, so this is not a desirable. Always we want to have something like this. So for that, we can implement a notch filter. So notch filter is something like this. Uh, it will have two poles. Okay, so two poles on the real axis and two zeros. There is actually designed so that it is nearby those high frequency poles so that they can actually go towards each other and it can cancel each other. So influence of this one is minimum and then you can have a response like this. So the book has given, so we discuss it, but it will be more important while you're actually dealing with physical systems like the high frequency system that we have discussed here, mechanical system. So if you have something like that, then you can have your notch filter to eliminate the effect of those. Okay, so now this is your summary table. So in the summary table, as you can see that the PI controller, how it works, you have a pole at the origin and then you have a nearby zero. And then you have a another way to improve the steady state error is the lag compensator. Now you have a pole that is close to origin and a nearby zero. And a PD controller, a pure derivative controller, and also you can have your transient behavior improvement. Another way is the lead compensator, and that is you have a zero. This time zero is closer to origin, but not that close, but comparatively closer to the origin that your pole. So as you can see, these two are actually same transfer function. There is hardly any difference between these two transfer function. Only the fact is that here your PC is smaller than ZC, and here your ZC is smaller than PC. Which one is closer? So if PC is closer to the origin, then it is a, a lag compensator, and if your ZC is closer to the origin, then it is a lead compensator. Okay, now finally the combination of both of them, improving both transient and steady state behavior. So for that you have ideal case PID controller. So you're designing something like this. These are actually for integral. This is for your derivative, and as you can see, they are identical. Okay, so only the difference is whether the pole is closer to or the origin or zero. But there is another difference actually. This is one thing that pole zero closer to the origin or not. But for the lag one, there actually has to be very close, and this actually has to be slightly far away so that we can have our second order approximation. Okay, so this is the only difference. Okay, so this is your cascade compensation designing. So now we have another one that we have said that we have the feedback design. So I think it is almost 1 hour. So if you go further, it will be difficult to catch. So rest of the thing we'll try to, I'll try to make another video quick as possible, and then I'll try to upload it because after this chapter, we have two more topic left in this chapter. That is 9.5, that is feedback compensation, and 9.6, that is physical implementation, realization using your op-amp active and passive networks. So that one I'll try to make it maybe by Friday or Saturday morning. Then I will try to upload. Then maybe I have to start the chapter 10 and chapter 11. I'm not sure how far I'll be able to go. So, okay, let us end the class here. See you in the next class, inshallah.